morning to all of my students. Today I will deliver lecture number 7 and I will discuss about ordered sets, partial ordered sets, total ordered sets, semi-lattices and lattices, and some relevant results. In this lecture we will do this, and after this lecture unit 1, by the end of this lecture unit 1 will be finished. So let's start. Lecture number 7. Definition. Start with definition. Let X be known in the subset. Then binary relation R on set X is called partial order relation. Is called partial order if binary relation means what? R is a subset of X cross X. We say that R is a binary relation on a set X if R is a subset of X cross X, correct? So then the binary, when we say that this binary relation is a partial order on set X if number 1 X or X, for every X belongs to X, if this is true, and every element is related to itself. Second, X or Y and Y or X implies X is equal to Y. Whenever such a situation arises, that when X is are related to Y and Y is related to X, are related to X of course, then X and Y becomes equal. And that property, of course, that is called reflexive, and that property is called antisymmetric. And third one is transitive, that is X or Y and Y or Z implies X or Z. That property is called transitive. So R should be transitive. So you can say that when binary relation R is reflexive, antisymmetric as well as transitive, then we say that relation R on a non-empty set X is called partial order relation. And we denote partial order relation R on X by the sign, like this. So we say that X, this is partial order set. A non-empty set with partial order relation is called partial order set. In short, we say that it is POSET, that is partial order set. Now what could be the example? If you see what could be the example, you see that the example, if you take like this set of natural numbers, and this is partial, this is the relation on N, and we define like this: A less than B if and only if A divides B, correct? Then this set is what? Partial ordered set. This is the example of partial ordered set, correct? That is, we define relation this A is less than or equal to B, A are related to B, if and only if when A divides B. So you can just verify all this, that this relation is reflexive as well as antisymmetric as well as transitive. So this is the example. Now next definition is that a partial ordered set, just I write in short, POSET, a partial ordered set is called total ordered, if for any xy belongs to X, either X is related to Y or Y is related to X. So when we say that partial ordered set, a totally ordered set, a partially ordered set is totally ordered set if we have this extra property. Along the properties of partial ordered sets, we have extra property. What is the extra property? That is, for any xy belonging to x, either x is related to y or y is related to x. X less than equal to y or y less than equal to x. Now you see the example. Example is what? Example is set of natural numbers. And this is the relation, and this relation is what? This is just the natural order. Isn't it? Natural order. So this is natural order. Well, all of you can see that either, if you, for example, if you take any two natural numbers, you can see that either one natural number is less than another natural number, isn't it? So this order is the usual order, natural order. So this is the example of totally ordered set. Now we move to next definitions. That y be a non-empty subset of partial ordered set. An element A belongs to Y is called minimal if for every Y belongs to Y, Y less than A implies Y is equal to A. Correct? So this is the example. Y be a non-empty subset of partial ordered set X. An element A belongs to Y is called a minimal element. Is called minimal element if for every Y belongs to Y, Y less than equal to A implies Y equal to A. It means what? It means there is no element in Y, isn't it? There is no element of Y that is strictly less than A. So whenever Y less than equal to A, it implies Y is equal to A. So what is the example? See about the example. First you consider set like this. You consider the set and define A like this, such that A divides B. You know well this is what? This is partial ordered set. All of you know well. See, all of you can verify that every prime number is maximal, or every prime number is minimal element. Correct? Every prime number. You take any subset of natural numbers and operation is same like this, A less than equal to B. If and only if A divides B, then all of you can verify this, that every prime number is minimal element. This is the example of minimal element. Now we move to the next definition. So as we have defined minimal element, we can define a minimum element. What is a minimum element? In a similar way, like Y be, you take non-empty subset of partial ordered set X. This is partial ordered set. Okay? This I am writing in short. So an element B belongs to Y is called minimum element. element if y less than is equal to a for every y belongs to y. This is the fact. This is the definition of the minimum element, that is this side. I wrote reverse inequality. So A is called B in fact, B is. So B is called minimum element if B is less than or equal to y for every y belongs to y, then it is called minimum element. Now try to think about that. What is the relation between minimum element and minimal element? What is the fact regarding this? So fact is that, just write first I want to give the example here for that. What would be the example? You take a set of natural numbers, take this as the usual order. If you take like this, this is partial order set, of course. Isn't it? This is the usual order, natural order. You can see that one is what? One is minimum element. Of course, one is minimum element in this partial ordered set. Correct? Now, the fact is that every minimum element is minimal. Every minimum element is minimal, but converse is not true in general. But converse is not true in general. Every minimum element is minimal, but converse is not true in general. So for this, you have to verify it. First you have to prove that every minimum element is minimal, and to prove converse is not true in general, you have to give the counter example. So let's see. Let A belongs to Y. Y is not only subset of partial ordered set. This is partial ordered set. Correct? So let A belongs to Y. This is a subset of partial ordered set. Correct? B minimum element. That is what we have. Well, that is, we have A less than is equal to Y for every Y belongs to Y. This we have, correct? This we have. Now, what is our claim? Our claim is to show that A is a minimal element. So then, if we take Y less than equal to A, now you see, if you take Y less than is equal to A, then you have to see either Y is equal to A or not. What is your claim? Claim is what now? Claim is Y is equal to A. If Y less than equal to A implies Y equal to A, then A becomes what? Minimal element. So yeah, it's obvious, because A less than equal to Y, Y less than is equal to A, and we are in partial ordered set, correct? In partial ordered set, if substitution arises due to antisymmetric property, Y and A becomes equal to each other. So since X is partial ordered set, therefore Y less than is equal to A and A less than is equal to Y implies Y is equal to A. So A is minimal element. So in this way, this fact is proved. Correct? Now, what about example? Example, you can see, well, as we have seen already, that in set of natural number, if you define operation like this, A less than B, then only if A divides B, well, you can see that every prime number is minimal element, but every prime number is not minimum. Correct? It's not minimum. Only one is minimum. Here what? You can see that every prime number is minimum, but not minimum, because minimum element is in this is only one. Correct? So in this way we have verified this. We have verified the fact. Correct? Now we move to our next result. That if we discuss about if Y, a subset of partial ordered set, is totally ordered, then terms minimal and minimum both are same. Correct? So we will do the same thing here. That is proposition 1.3.1, page number 13. What is that? Let Y be a non-empty subset of partial ordered set X. Then Y has at most one minimum element. Second, if Y is totally ordered, then the terms minimal and minimum are equivalent. The terms minimal and minimum are equivalent. This is the problem, that Y be a non-empty subset of partial ordered set X. Then we have to show that Y has at the most one minimum element. So for this, well, you can assume that it may have, just assume that it has two minimum elements. So prove that Y has two minimum elements, correct? Two minimum elements, say A1 and A2. Say A1 and A2. Then purely from the definition of minimum, what you have? Then it's purely A1 will be less than equal to A2 and A2 less than equal to A1. This you have or not? Because A1 is less than equal to Y for every Y belongs to Y, and A2 less than equal to Y for every Y belongs to Y, correct? So of course A1 will be less than equal to A2 and A2 less than equal to A1. No, we we are dealing with partial ordered set, and due to anti-symmetric property, what we will get? A1 less than equal to A2 and A2 less than equal to A1. What does it imply? As X is partial ordered set, we get A1 is equal to A2. Because A1, A2 are the members of Y, and of course Y is a subset of partial ordered set. Of course it will be partial order. So due to anti-symmetric property that A1 less than equal to A2, A2 less than equal to A1, we get A1 equal to A2. Correct? Isn't it? We also just write since A1 less than equal to Y for every Y belongs to Y, and A2 less than equal to Y for every Y belongs to Y. This you have. So in this way, we have proved that Y has at most one minimum element. Now let's do second part. What is second part? They are saying that if Y is totally ordered, then terms minimal and minimal and minimum are equivalent. See, we have already proved that every minimum element is minimal. It's true. It doesn't matter whether set is partially ordered or totally ordered. In every case, every minimum element is minimal. Just we have to prove the converse in this case. That is given Y is totally ordered subset of partial ordered set partial ordered set X. Okay? This you have. Now let A belongs to Y be minimal element. This is a minimal element. That is Y less than equal to A implies Y equal to A for every Y belongs to Y. This we have, correct? Now what we have to prove? We have to prove that this minimal element is minimal. Claim is what? A minimum. We have to prove minimum. So what is the claim?